So here we go with the second video on section 4.2. This one will deal with the mean value theorem instead of Rolle's theorem. Now, the mean value theorem follows Rolle's theorem. In fact, Rolle's theorem is used to prove the mean value theorem. We're not required to prove the mean value theorem. We're just required to utilize the mean value theorem and to understand the mean value theorem. So here's a quick overview of the mean value theorem. The mean value theorem says if you have a function f, and in a manner very similar to the hypotheses of the Rolle's theorem, the mean value theorem requires that the function f be continuous, again on a closed interval a, b, and it requires that f again be differentiable on an open interval a, b. Now we have the same facts about differentiability here that we had on the Rolle's theorem. We can't be differentiable on a closed interval because the derivative doesn't exist at the endpoints of a closed interval. Remember, the derivative is a limit. A limit requires two sides. If we close the interval, we don't have two sides. We don't have a left-hand side at A. We don't have a right-hand side at B. So, given that, we know then that the mean value theorem has two of the three requirements for a function that we had to satisfy in Rolle's theorem. Now, when we get to actually working out problems with the mean value theorem, we'll see that we go through exactly the same steps we went through with Rolle's theorem. We satisfy first the condition of continuity, so we show continuity on a closed interval, again perhaps using our theorems rather than the definition, and we again show differentiability. We show the derivative of f exists on the open interval from a to b. So those are our two conditions for the mean value theorem. Now, the mean value theorem, unlike Rolle's theorem, the mean value theorem says that if those conditions are met, then there exists the c. Oh, wait a minute, that sounds a lot like Rolle's theorem. But there is something different. There is a difference. It says, yes, there exists a c in the open interval AB. So that's the same as Rolle's theorem. But now the condition on that c is completely different. Rolle's theorem said that the derivative at c had to be 0, somewhere between A and B, exclusive of the endpoints. While the mean value theorem says there's a c in the open interval from A to B, but this time instead of the derivative at c equaling 0, the derivative at c is going to equal the slope of the secant line going from the points A f of A to B f of B. So what it says is that somewhere between A and B, the slope of the tangent line to the curve f is going to be equal to the slope of the secant line that connects A f of A and B f of B. Now that's a different conclusion from Rolle's theorem. Rolle's theorem said someplace the derivative was going to be 0. But as I showed you in class today, to get from the mean value theorem back to Rolle's theorem doesn't take a lot of effort. Rolle's theorem is a corollary of the mean value theorem. So if we're going to solve problems 11 through 14 in the homework, then we're just going to go through at least in the beginning, because the first part of the instructions state, show the conditions of the mean value theorem are satisfied. So we're going to go through very similar analysis to what we did for Rolle's theorem. So if we pick one of the problems, we have 11, 12, 13, 14. 11 and 12 are both polynomials. We know polynomials are everywhere continuous and everywhere differentiable. So having a conversation right now here in this format about those two problems, well, it's kind of a waste of time. So let's look at either problem 13 or problem 14. Now problem 13 is a radical, and we just did a problem with a radical. So let's address problem 14. Problem 14 says f of x equals x divided by x plus 2, and the interval that we're given to consider is the closed interval from 1 to 4. And the instructions here are very similar to the instructions we saw in problems 1, 2, 3, and 4 regarding Rolle's theorem. Here, we're going to first show the conditions for the mean value theorem are satisfied, And then after we show the conditions for the mean value theorem are satisfied, then we're going to find the C that the mean value theorem says exists. And again, there may be more than one, but we're going to find the C, at least the single C, that the mean value theorem says exists on that open interval. So we begin with our function f of x equals x divided by the quantity x plus 2, and we must show continuity. So how do we go about showing continuity? Well, we have several theorems, one of which is going to be very, very useful here. We have a theorem from back in chapter 2 that says that if a function is either a polynomial, a trig function, or a rational function, or a root function, the theorem says that that function is continuous on its domain. So if we look at our function, remember, is x divided by x plus 2. Well, the domain of f is the set of x's such that x does not equal negative 2. That's the domain of our function. It's the set of x's such that x does not equal negative 2. Well, if you look at our interval, negative 2 is not in our interval. So we can use that theorem from back in chapter 2, that theorem about continuity that said rational functions are continuous on their domains. Well, the domain of our function contains the closed interval from 1 to 4. Thus, our function is continuous on the closed interval from 1 to 4. So, by a combination of that theorem and the fact that negative 2 is not in the interval they asked us to consider, we can say, therefore, f is continuous on the closed interval from 1 to 4. Now, on a test or a quiz, you would have to write down a statement. You'd have to say something about the theorem and how the theorem says rational functions are continuous on their domains. Then you'd have to link that to what is the domain of your function, in this case, everybody except negative 2. And then you'd have to state, hey, negative 2 is not in my interval, therefore my function is continuous on my interval. So it's not simply something that you can think through or have a conversation about like we are right now, and then just write down, and therefore continuity is satisfied. We've got to put something down to substantiate that. The second condition of the mean value theorem, remember, is the second condition from Rolle's theorem. It says the function has to be differentiable on the open interval from 1 to 4 in this case. So the first thing we're going to have to do is we're going to have to find the derivative of this function. Now that's going to involve the quotient rule. So we're going to have x plus 2 times the derivative of x, which is 1. So x plus 2 times 1 minus the numerator is x. The derivative of the denominator is 1. So x times 1 all divided by the denominator squared. If we do the algebra to simplify that, we end up with 2 divided by x plus 2 quantity squared. So our derivative is 2 over the quantity x plus 2 squared. Now, we have to show the function is differentiable on the open interval from 1 to 4. The open interval again, right? I know I keep harping on that, but it's really important that we remember differentiability has to be on the open interval because the derivative is not existent at the endpoints. So from here, what do we say? Well, we say that the derivative is 2 divided by the quantity x plus 2 squared. Differentiability says the function must exist. The function's derivative must exist. Well, our function's derivative exists everywhere except negative 2. So f prime of x fails to exist at x equals negative 2. But x equals negative 2 is not in the interval (1 to 4) open. So, therefore, our function f is differentiable on the open interval 1 to 4. So, we would write something similar to this. f prime of x fails to exist at x equals -2, but x equals -2 is not in the open interval from 1 to 4. Therefore, f is differentiable on the interval 1 to 4. With those two steps, we've satisfied the conditions for the mean value theorem. Now that we've satisfied the conditions for the mean value theorem, that means that the conclusion of the mean value theorem must therefore be valid, or there is going to be a c, a number between 1 and 4 where the derivative at that number is going to equal the slope of the secant line. So we begin by finding the slope of the secant line. Now we have a function. Remember, our function is f of x equals x over x plus 2. Our interval is the closed interval from 1 to 4. So I have to find the slope of the secant line from 1 to 4. Therefore, I have to find the points. Well, when x equals 1, f of 1 is 1/3. You plug 1 into f of x, you get 1 over 1 plus 2, that's 1/3. When x equals 4, f of 4 is 4 divided by 6, or 2/3. So we now know f of 1 is 1/3. We know f of 4 is 2/3. So we use the slope formula to find the slope of the secant line. So the slope of the secant line equals 2/3 minus 1/3 divided by 4 minus 1. Now if we simplify that, 2/3 minus 1/3 is 1/3, and now 4 minus 1 is 3. 1/3 divided by 3, well, 1/3 divided by 3 is 1/9. So the slope of our secant line is 1/9. That means our task is to now find a place, a point between 1 and 4 where the derivative equals 1/9. Now we know what the derivative is. We earlier found that f prime of x was equal to 2 divided by x plus 2 squared. Our job is to see when 2 divided by x plus 2 squared, the derivative, when does that equal 1/9? So we set up that equation and we solve it. If we cross multiply, we get x plus 2 quantities squared equals 18. We take the square root of both sides. We get x plus 2 equals the square root of 18. Now, I only need the principal square root. I only need the positive square root because my interval goes from 1 to 4. So, strike that. That may not be right, but we'll come back to that. So, when we move over the 2, we get x equals 2 negative plus the square root of 18. Negative 2 plus the square root of 18. Well, that means we get negative 2 plus 3 root 2. The square root of 18 is 9 times 2. The square root of 18, therefore, is 3 root 2. Negative 2 plus 3 root 2 is within the interval from 1 to 4. And therefore, that is the point C that the mean value theorem promised us we would find. Not a pretty point, but it's a point. There's a place between 1 and 4 where the derivative equals the slope of the secant line. So those are the direct application problems. The previous video does the direct application problem of Rolle's theorem. This video does the direct application of the mean value theorem. Tomorrow in class, we'll continue with these two theorems and see just what interesting things in the world of mathematics can we find or discover or verify using these two theorems. But tonight's homework, that's not the theme of tonight's homework. Tonight's homework is, can you apply the theorems and find the point C in the open interval? I hope this helps. I'll see you tomorrow morning.